Okay. Make sure that this is muted. Let that going. That go away. Make sure that that is muted. Good. Okay. All right. So what happened? What had happened is this is going to be the actual review. The other one we did in class, yeah, got lost. Question 5. Find the antiderivative of for the function, oh my gosh, f of x equals e to the tangent of x. I'm going to write that down. And then also share with you what I'm writing down. So, oh, that's backwards. That's bad. Hang on a minute. Why would you be backwards? We'll resolve this in a second. General. Camera switch. Good. Close. No, that would do it. That didn't do it. Select the camera. Yes, that's the one. That was bizarre. Okay, I think we're ready. Okay, so f of x, you saw that, right? That it was backwards. Weird. All right, so f of x equals e to the tangent of x over cosine squared. And in this question, when we discussed it or are discussing it now, the situation we have to identify here is that this is a U substitution problem, but it would help if we would rewrite this. And I'm going to show the middle step along the way before we do the U substitution. So the first thing I'm going to do is write e to the tangent of x as its own factor. And then I'm going to write 1 over cosine squared x. This is not necessary for you to write or for anyone to write, but I'm just trying to explain it right now, what's going on. Since e to the tangent of x is its own factor and 1 over cosine squared x is actually known as secant squared x, that little detail might help us identify what our u substitution should be. We use a u substitution and also a du substitution here because it's kind of like we're doing a chain rule for integrals. So in the chain rule for derivatives, you do the outside derivative and then you do the inside, and then you further on chain derivatives of inside and more inside and more inside functions. With this one, we want to think from the inside out and also recognize where there's like a derivative already. This is like the derivative that we can spot. So the derivative of secant, no, flip that. The integral of secant is tangent. That tells me that tangent should be the u sub. And that also says that du should be the derivative, du dx. There we go. So I'm going to rewrite this as e to the u du. And u is tangent, du is secant squared. So integrating this dx, integrating this dx, integrating this dx means I'm going to integrate this. Dx is taken care of in the u substitution and the du substitution. So we really have the integral of e to the u plus c, and we can put u as in tangent of x back in. Okay. All right, next up, we're going to be talking about the integral. Let me go ahead and take care of some. There we go. Okay, so with question 6, find the integral of x to the third of multiplied by the radical 2x to the fourth plus 1. And then it's dx. This is still a u substitution problem. In this problem, still thinking chain rule, thinking not outside, inside, further inside, but actually in reverse. This square root symbol is containing an expression. So there is an inside function. In the chain rule for integrals, we should think about identifying what is the most inside or what is an inside function. That's a weird equal sign. So we're going to call u the thing under the square root. That's usually how we identify it. We look for some larger structure and then think about what we can do to manipulate that larger structure, like the square root of something. The thing inside square root is probably going to be the u substitution. There are some times where a u substitution doesn't actually fit where we would think, or we'd be like, oh, for real? That's what? And then stuff happens. But in this case, no. 8x to the third dx. Yeah, definitely. Okay. So what we already have, and I feel like I need like the highlight or something, or call attention. Yeah, my highlighter. That x to the third and dx, x to the third and dx are already in the integral. What's missing is 8. So put it in there. 8. Readjust the camera. There we go. You can't just add a constant, because then you've scaled up everything. Every answer has been multiplied up by 8. So in order to rectify the added constant, we have to also put its reciprocal. You could put the reciprocal 1/8 inside, but you're going to bring constant values. You should bring constant values out in front of the integral anyway. So 8, that takes care of the 8 that we needed. And then its reciprocal 1/8 on the outside. That'll help balance everything out. So we have the reciprocal 1/8, there it is, times the integral. Now 8x to the third dx, we can rewrite as u. And 2x to the fourth plus 1, we can write, I'm sorry, du. And then the 2x to the fourth plus 1, we can write as du. So this is the integral of the square root of u du. If you remember the direct shortcut for square roots, integrals of square root, good. If you forgot it, we can kind of build it. If we, instead of writing it with a radical, we write it as an exponent, a fraction exponent. So u to the 1/2 du. That way we remember what we do with exponents. You add 1, flip it, the whole how you apply the exponent to the property. So this is going to become 1/8 times 1 over, well, let me do the exponent first. 1/2, we're going to add 1 to the exponent, making it 3/2, which means 3/2 goes on the bottom, plus c. Fraction under a fraction. Multiply by 2/3. Flip and multiply is the nice abbreviated shortcut for this. So we really have 2/24, 2 times 1 times 1, 3 times 8. U to the 3/2 plus c. And if I finish the problem out, 1/12, right? 2/24 is 1/12. And then I'm going to use parentheses. I'm not going to reverse this back into radical form. You could. I don't want to. I think it's actually a mess. 2x to the fourth plus 1 to the 3/2 power plus c. There we go. Yeah, awesome. Okay, question 7. Now, integrating by parts is a whole thing, right? So number 7, find the integral x squared ln of 2x dx, integrating by parts. Hold up a second. Let me check how things are going with the live stream. All right, that's me looking at me watching a live stream. Excellent. Now, find the integral x squared natural log of 2x dx using integration by parts. The thing that we can do here is we can use this acronym when a integration by parts problem comes around. You must lip it. So we're looking for the choice in our setup. Something I saw happen in one of the channels I follow. The instructor there, he wrote the D and the I for differentiation and for integration. This is our U sub and our dV sub in the integration by parts formula. Remember, integration by parts is uv minus the integral v du. If we can figure out what part of this is the u, that's what Lippitt tells us, and what part of it is the dv, then we can just set our structure up and also keep change. Okay, so logarithms, inverse trig, polynomials, exponentials, and standard trig functions. So we're going to choose logarithms as our u. So natural log of 2x, and then the other x squared dx. That is our setup. It looks like natural log of 2x would be the one to choose. Give me a second. So that setup is telling us that we're going to do 1 over 2x using L for logarithms, and then using the chain rule on logs of 2x times 2. Hold up, I got a student here. Not ready. Okay, so then the 2, as in the chain rule on the inside of the function, is set up. Bring that window out of the way. The ln of 2x gives us 1 over 2x for its derivative. The 2 that's here is the chain rule on the inside, so we're going to cancel them out, giving us 1 over x. Lipids, the rest of the situation over here, we don't really care about, right? We don't need to identify it cleanly. It's just x squared. So the integral of x squared is 1 over 3 x to the third power. There's some explanation there that we can go into. That's just a standard polynomial antiderivative. Trying to manage life during the day. I'll come back after our announcements.
Good morning.
Sweet. Friday announcements, super short. Whenever you're watching it, whatever. But for me, good day. Now, in this structure, Nope. Here we come back. Okay, maybe we're back. So the setup, getting to the point of this problem. Thank you for your patience and skipping through, I hope. You take the U and the V, because that's what's set up. This is dV, this is the V that fits our formula. U times V, then minus the integral V du, that's this integral. Well, we'll set it up that way, and then we'll see how much we have to continue using. So U times V is 1/3 x to the third times the natural log of 2x. Then minus the integral, so minus the integral 1 over x, don't forget the 2's canceled, times 1/3 x to the third. Oh, there's also a dx here at the end, so I need to make sure that I bring dx into the integral. Kind of missed that point if you don't catch that along the way. I'm glad I mentioned it now. Okay, so the 1 over x and the x to the third power, these will reduce to x squared. The 1/3 that's right here, we can bring that all the way out front of everything, which means this is 1/3 x to the third times the natural log of 2x minus 1/3 times the integral of, well, what's left? What's left on the inside is x squared dx. The integral of x squared, we've already had the reason to discuss this. That's kind of why this question was nicely written this way. We know that the integral of x squared is 1/3 x to the third. So substitution for this integral with what it evaluates to, and we're left with 1/3 x to the third natural log of 2x minus 1/3 times 1/3 x to the third plus c. This part right down here, however it's shown up on your screen, this part down here, 1/3 times 1/3 x to the third, that is the whole integral structure. That is the replacement. Writing it cleanly and nicely, I guess what you could do, you could even factor this out of both terms. We would have 1/3 x to the third times the natural log of 2x minus 1/3 plus c. You could write that expression and be done. It might be difficult to grade or it might be difficult to read. So maybe we don't factor out the 1/3 x to the third. It's just nice to know that it exists. I guess we could probably write it as 1/3 x to the third natural log of 2x minus 1 over 9 x to the third plus c. Pick your favorite statement. I like acknowledging that this second one right here exists, but this is probably the better answer to report with no parentheses. Okay. Okay, that's question 8. And so I'm going to do what I can to bring, or sorry, that's question 7. I'm going to get ready to do question 8. All right, we did question 8 in class. Whenever we've done question 8 in class, it is a long problem. Okay. let's see here. Let's go question 8. Question 8, integration by partial fractions. So here we have the integral of 3x plus 2 over x squared minus 9 dx. And with this question, we know that it's a partial fractions response because we have a rational function. There's some structure to this that will let us take this rational function, this rational expression, and break it up into two or more, fractions, where the denominator of each fraction is some factor of this original denominator. So let's just focus on the original denominator, x squared minus 9. If you factor that, you may remember or recognize that this is a difference of squares problem. I mean, for example, you can go x squared minus 3 squared to have the same situation. And if it's squared minus squared, it is directly a difference of squared problem. So that would create x minus 3 and x plus 3. And if you need to prove it, part of the difficulty of calculus is not in the calculus itself, it's in the algebra that's along the way. X times x, x times 3, negative 3 times x, and negative 3 times 3. Plus sign, I meant to write a minus, but minus 9. And then you can see that the plus 3 and the minus 3, they cancel out. So yes, we've found our factors. We can take that information back up to the original problem. We can write it as the integral of something over the first factor, x minus 3 dx, plus the integral of something else, maybe the same value, I don't know, over the second factor, x plus 3 dx. If we can just figure out what the first value is, this is a number, by the way. Sometimes they're an expression, but for us, this will be a number. And this one over here as well. This is some expression, some number. We don't know what it is yet, but if we could figure that out, that'd be a super easy integral to calculate, to determine. I mean, for one thing, this is a some number over an x. You're probably talking a natural log. Remember, the antiderivative of 1 over x is the natural log of the absolute value of x. That's the goal then. The goal is to figure out how, I'm going to use A's and B's, A and B. The goal is to figure out how A over x minus 3 plus B over x plus 3 is going to wind up being equal to 3x squared plus 2 over x squared minus 9. If we can figure out what A is and what B is, then this partial fractions problem is done. All right, well, let's set it up. Since we have two fractions, different denominators, the only way to combine fractions is to have the same denominator. So A as a fraction, its denominator is missing the piece that we multiply together to make x squared minus 9. So we need to multiply this denominator by the other denominator. And of course, in that process, top and bottom, same thing. That creates x squared minus 9. B as a fraction is missing the exact same thing. X plus 3 needs x minus 3 in order to have a common denominator with the other fraction and a common denominator with what's over here. So if I put x minus 3 times x plus 3, we will have x squared minus 9, but it's not balanced until you put it on the top of the fraction there. Okay. A times x plus 3 plus B times x minus 3. All of these now have the same denominator, x squared minus 9, because it's a common denominator and it's a common denominator, so add the numerators. This still equals, though, 3x plus 2 over x squared minus 9. And you know what? If the same denominator, x squared minus 9 and x squared minus 9 shows up on both sides of the equation, I mean, you could think cancel, you can think multiply both sides by x squared minus 9, but in reality, the denominators being the same tells us that a times x plus 3 plus b times x minus 3 has to equal the answer, the 3x plus 2 value. So for that reason, we're going to go ahead and ignore the denominator, or just acknowledge that it exists, but it's not a factor in our calculation any longer. It's set up the equality, both sides of the equation being equal. So now I'm going to go a times x, a times 3, b times x, b times 3. Let's go ahead and distribute, get rid of the parentheses. Ax plus, I'm going to put 3 first, plus bx minus 3 goes first, equals 3x plus 2. Now I have a highlighter, or this thing. The things that are x's are like terms. Let's combine them. Ax plus bx. Those two together on this side of the equation can further be factored to be a plus b. They both have an x factor, right? So factor out x from both of them. A plus b is what's left. And I guess a double underline, I'll circle it. Circle and circle. Those are just numbers. They don't have an x factor, so they're just constants. A is a number, b is a number. When you multiply by 3 and by negative 3, you get a number answer when you're done. I'm going to factor 3 out of it, though. Plus 3 times a minus b equals 3x plus 2. You know what? A plus b is a number because a and b are numbers and we're adding them, and it's in front of x, just like the 3 on the other side of the equation is in front of the x. So if we go a plus b equals 3, that's this relationship right here. The a plus b is a coefficient of x. The 3 is a coefficient of x. They have to be equal. And also for the same reasons, a minus b and 2, 3 times a minus b and the 2, those together also are factors. Like they are similar things. And on both sides of the equation, the things that are similar things, we are going to set equal to each other. Okay, solve for a. Solving for a up here, easy enough. Subtract b from both sides. A equals 3 minus b. And since we know what a equals, 3 minus b, down here, we can replace a with that thing. So 3 times 3 minus b, that equals 2. We need to get b by itself. So a little further solving. We have, let's see here. I have another, running out of panels. Let me check my desk. I will do this then. Okay. So continue to solve for b. I probably should have just left the 3 alone, but I'm going to acknowledge it anyway. So 3 times 3, 9. Negative b minus b is negative 2b. So 3 times negative 2, negative 6b equals 2. Subtract 9 from both sides. Negative 6b equals negative 7. b equals 7 over 6. There we go. We have our coefficient of b, 7 over 6. And let's go back up to the original. Let's put 7 over 6 right here. No, let's put 7 over 6 right here. 3 minus 7 over 6. Let's see, 3 is over a 1. So if I want to get a common denominator, multiply by 6, I'd have 18 minus 7 over 6, 11 over 6. That's a. With both of these coefficient values, the fact that a is 11/6 and b is 7/6, we can go all the way back to, well, not the original integral, but go back to the a integral and the b integral and put those values into them. So that means I'm going to write this as, again, this is a 4-point question, but it'll make your brain kind of hurt along the way. A, we said, was 11/6, okay, over x minus 3 dx. B, we said, was 7/6 over x plus 3 dx. See if I can get both of those on here. Zoom out a little bit. Yeah, so here's the broken apart partial fractions integral. And here's what we get when we've done this whole process in the middle to find what a and b actually are. Let me rewrite this a little more cleanly. In fact, because this 11/6 and this 7/6, they're just constants, we can bring them out front. Oh, big brain moment. I'll share it with you in a second. Maybe you can already beat me to the answer there, what I might be thinking about. X minus 3 dx plus 7/6 integral 1 over x plus 3 dx. By the way, here's what I'm saying. We'll return back to that problem in a second. But if we're saying that this is the original integral, it's going to break apart into factor 1, factor 2 with a b on top and an a on top. I don't know, letters. Letters is all there. They're just space holders and tell me what they want to be. Eventually a, this is not always true, but it's pretty true most of the time. We could move a in the front, 1 over x minus 3 dx, because a is supposed to be a number. Certainly in this example is a number. I can't say it's true all the time, but definitely in this one, it might be like a shortcut that would help keep things clean. We still have to go figure out what a and b are, but they're eventually going to be moved out to the front of everything. And because they're moved out to the front of everything, it might be nice just to kind of treat them as such. See, a there, b there. Okay. 1 over x minus 3. This is a u sub. Dx is d, or du is dx. So this is going to become 1 over u du. What's the integral of 1 over u? It's natural log. So equals 11/6 times the natural log of at the absolute value of u. Over here, the same thing. U, different letter. I know it's written the same, but it means for this problem, the u sub is x plus 3. So du is still dx. That's going to become a u. That's going to become a du. It's the integral of 1 over u. Natural log again. Different coefficient. Natural log of u plus c. Put the respective u's back in the problem to get our answer. Survey says, oh my gosh, so much paper being used for this one. 11/6 times the natural log of x minus 3 plus 7/6 times the natural log of x plus 3 plus c. Call that our answer. Get out of here. All right, let me pause and I'll get ready to do question 9. All right, let's see here. This is question 9. Question 9 using trig subs. And if you've seen enough of these questions, maybe you've attempted the required standard for this one, R6, then you have the opportunity to see kind of where I'm going with this and know what to expect when this similar question pops up in a stressful setting. Here we have the integral of 9 minus x squared, square rooted dx. And you might think, can I just do a u substitution? Now, this is wrong. Don't copy this down like it's what you're supposed to do. But let me show you what happens. Let's say u equals 9 minus x squared. That means du has to be negative 2x dx. The negative 2 is easy enough. You just throw the value negative 2 into the function, and it's reciprocal out front. That way everything stays balanced. But x is a function, and it has so much variability that the constant, the nature of a constant function, that's easy to explain away. We've just made everything be twice as big, and then we make it be half the size, and it kind of like balances out. But because x can be any number, it's not a constant. You can't just throw an x and then 1 over x into the problem. That is, nope. Hang on a minute, let's bring it back here for effect. Can't do that. So you go through your checklist and you think maybe partial fractions. It's not, there's no fractions here. And you think, what about UV, the whole integration by parts? Doesn't exist here. 9 minus x squared as a square root. Okay, this is the last integration technique that you need to know out of many, many others should you go further on in your math career. If you spot the structure of this problem and you think, man, that vaguely looks like a equals c squared minus b squared square rooted, I wonder what I can do with that. Which, by the way, let me just make sure I got my structure right. A squared plus b squared equals c squared. If I subtract b squared from both sides, I get a squared equals c squared minus b squared. If I square root and then I square root, I have this. So recognizing that 9 minus x squared as that structure really looks an awful lot like the answer, although x is a variable, but it looks an awful lot like the answer to a right triangle problem, as in A, let's put it on the bottom here, 9 minus x squared. And then C, the 9 could be rewritten as 3 squared. So that tells us that C, the hypotenuse, is 3, right? See the structure? C squared is 9. So square root, C equals 3. C equals 3. And then X is the B side of this problem, right? So this expression really resolves nicely to be the sides of a right triangle. And in that right triangle, boom, boom, there's a theta angle. This is called trig sub for a reason. Because if we can identify 9 minus x squared, that square root expression generates x and 3. Sine of theta is x over 3. Super quick adjustment. Oh, while we're here, that means x equals 3 sine theta. Oh, and you know what? Even further, dx would be 3 cosine theta. Yes, it's all coming together. Taking that information, a little bit of overlap here on my letters, my words here. Since we identified this trig sub, that's the trig sub to spot. And as we identified that trig sub, x is 3 sine theta. Here is an x, so we're going to make it be 3 sine theta. Dx, d theta, dx is going to be replaced with 3 cosine theta, d theta. I'm going to write it out. Here we go. Equals the integral 9 minus 3 sine theta, put it in parentheses because it's an expression, times 3 cosine theta d theta. Decent, nice. A little simplification along the way, a little reminder of where it came from. So we have 9 minus 9 sine squared of theta. It's an expression that's square rooted.
multiplied by 3 cosine theta d theta. And I moved the 3 out to the front of the integral. Carrying on. 9 is in both of these terms. We're not doing calculus yet. We did a little trig. Now we're going to do some algebra. 9 times 1 minus sine squared theta is all being square rooted. Cosine theta d theta. Don't forget the 3 in the front. All right, cool. Okay. So if you have the square root of two things that are multiplied like this, like square root 9 and square root 1 minus sine squared theta, well, I mean, we can split them, right? You can split multiplication of a radical to become 2 radicals. So square root 9, oh, that's a 3. Oh, that can even be brought out front. And then cosine theta d theta. And of course, 1 minus sine squared theta over, or in the radical of that. Do you remember that 1 minus sine squared theta is the cosine squared plus sine squared identity? I mean, if I subtract sine squared from both sides, I get cosine squared theta is 1 minus sine squared theta. So here with this 1 minus sine squared theta, I can replace that with cosine squared theta. There's kind of an assumption that's being made here. We're going to acknowledge and ignore it. 3 comes out, so we have 9. 3 times 3 makes 9. The integral of the square root of cosine squared theta times cosine theta d theta. There's kind of like a work on the side break right there. Squaring a square root pretty much crosses out. Again, like I said, there's a little hesitancy. There's some hand waving math magic that I'm not going to explain for the sake of being succinct. But you have a cosine that's squared and then you square root it. We have a little bit of an issue, but we're going to also be like, this works. Okay. The y part. Squaring a square root. Cosine squared theta d theta. Interesting. Here we are at 9 times the integral of cosine squared theta d theta. And I'll be honest, at this moment, I'm not directly aware of what the integral of cosine squared is. So I'm going to look it up and maybe suggest this for your note card. Integrate cosine squared. Oh, dude, Google to the rescue. Integral, plenty of good videos out there. Ooh, some good stuff from a channel. So we can check out any of those. Let's see if an image gives us the equation. Oh, nice. Okay, so they use the, power reduction formula. Make a note here. So by power reduction formula, which is something you may have learned in trig. I know when I've taught trig, I'm like, it's all online. Just know they exist and consider memorizing them, but that would be really brutal for me to say you have to. I'm going to acknowledge all of this step is what's happening. They rewrite cosine squared x as the power reduction formula, 1 plus cosine 2x over 2. Then they integrate the fractions 1/2 and 1/2 cosine 2x. They know that the integral of cosine 2x is sine of 2x over 2. That is a U substitution formula. Then that tells us that we have 9 times 1/2 x plus sine of 2x over 4 plus c. And I wrote it, and I'll show it. Done. Magic. Ooh. Google. Okay, that's what's happening between this step and this step. And if you want to see it, go back in the video a little bit and watch it again. I'm going to try to do number 10 on this exam. Let me get that one set up. I'm going to go off cams for a minute, scrub forward in the video until you find question 10. Saving 10 for class. Thanks for hanging out for the rest of the video. Stopping this.